you watched the atomic symbols video, carry on here. If not, please go watch the atomic symbols video first. We're going to continue on with the atom and what we need, why we need to know all the pieces that make it up. So when we think about an atom, let's go back to helium. Let's look at helium-3 and helium-4. Protons in each of them, well, they're helium, so there are 2 protons in each. Neutrons in each of them, well, helium-3 has 3 total things in its nucleus. 2 of them were protons, so there's 1 left. 3 minus 2 equals 1. 1 left to be a neutron. For helium-4, there are 4 things in the nucleus. 4 minus 2, there's 2 left over. There are 2 neutrons. And in terms of electrons, well, they both have no charge, so they must have as many electrons as protons. So 2 positives and 2 negatives means that there are no extra positives or negatives. When we think of building these atoms, I've got a proton, a neutron, a proton, and 2 electrons around them. Versus proton, 2 neutron, proton, and 2 electrons. When you add more things to an atom, well, things have mass. They get heavier. A proton and a neutron are just about the same mass, but an electron is 1/10,000th or so. So more electrons doesn't really change the mass, but more protons and neutrons do. So when we look at these two, we actually think about helium-3 as having 3 atomic mass units, where helium-4 has 4, and we shorten them AMU, atomic mass units. The idea is just more protons and more neutrons means more weight. So if I had 10 things that were all helium-3, so 10 times helium-3, well, that would be 10 times 3 for 30 atomic mass units. But if I had 10 things and they were each helium-4, sorry, helium, I wrote hydrogen, or helium-3. If I had 10 things that were each helium-4, that would be 10 times 4 for 40 atomic mass units. So you could have 2 containers of the exact same number of helium atoms, but depending on what isotope you have, they would weigh different amounts. Well, additionally, if you mix them, what if I had 5 of them that were helium-3 and 5 of them that were helium-4? Well, 5 times 3 plus 5 times 4, so 15 plus 20, 35 atomic mass units. If I have a mix of the two, I get a weight that is a mix of the weights. In fact, if I average this, each helium looks like it's 3.5 atomic mass units. Why this is important is when you have a bunch of an atom, your mass is the average of the different isotopes. Like, you have to deal with how many of each isotope you have. So this makes it hard to weigh out specific amounts of atoms. And unfortunately, that's what we have to do. If I have carbon and I'm going to react it with oxygen so that I can make carbon dioxide. Right? Say you had something like charcoal, so nothing but pure carbon. I burn it in the air and it makes carbon dioxide. Well, for every single atom of carbon, I need 1 molecule of O2 in order to make 1 molecule of CO2. I can't have 1.5 molecules of oxygen. I can't have 3. I can't have 1. I mean, a half. I need exactly this. When atoms combine, they do it by number. None of our scales, none of our weighing devices count atoms. They tell us weight. They tell us grams or pounds. So I need to have a ratio of how much an atom weighs for how many atoms. We call this the mole. Remember that 1 mole, it's one of our units, was 6.022 times 10 to the 23 things. This is like saying 1 dozen is 12. Right? Or 1 century is 100. It's just a word for a large number of things, but this is how many things you have to have before you are on the human scales when you're working with atoms. If you had this many hydrogen atoms, it would weigh 1 gram. If you had 1 mole of hydrogen atoms, that is 1 gram of hydrogen. So it takes an enormous number of atoms before you're on the human scale. This is why we work with the mole. It's just kind of simpler to discuss. Well, let's think back to the periodic table. So let's go back. If we go and look at hydrogen, let's blow it up a little bit, and we see the atomic symbol. Down below it, you will notice a series of 4 or 5 numbers, depending on your periodic table, and the other ones have it. Lithium says 6.938, beryllium says 9.010 or 0122, sodium is 22.990. They all have some number underneath them. What that number is the mass in grams for 1 mole of that element. So hydrogen is 1.0079. 0.079. Helium was 4.00. If you look up carbon again, carbon is 12.01. That number underneath, that is the mass, so the grams for every 1 mole. So like I said, if you had 1 mole of hydrogen, it weighs just about 1 gram. There's a little bit extra though. What that actually comes from is when I had hydrogen, remember there was H1, but there's also some H2, and there's actually a little H3 on Earth. The vast majority is H1. 1 proton, 1 atomic mass unit. But there's just a little bit of H2 and a really tiny little bit of H3. And so they raise the average a little above 1. When you find hydrogen on Earth, it comes as a mix. They have been mixing for 4.5 billion years. It is already mixed up. So you get 99.99% hydrogen 1. You get 0.007% hydrogen 2, and you get 0.003 or less percent hydrogen 3. In fact, it is quite a bit less in reality. But that little bit of heavier elements raises our weight just very slightly above 1. And what we find is that the average mass that you need for 1 mole on Earth is actually slightly above 1. So all of those weights on the periodic table, all of those numbers underneath the symbol, we have already done the math for the percentages on Earth. Carbon is mostly carbon-12, but with a very little amount of carbon-13 and carbon-14. So its average is slightly above 12. Helium on Earth is basically exclusively helium-4. So it's spot on right about 4.00. Other elements, some are spot on. If you look at oxygen, it's 16.00 in most books. But if you look at something like sulfur, just below it, sulfur is 32.06. It has a little bit of manipulation to raise it due to some isotopes. This is actually different on every planet. If we ever go to Mars and we set up chemistry, we will have to have a periodic table of the elements on Mars. We will actually have different averages on different places. This is actually really useful because when meteorites crash to Earth, we will actually take, if we find them, we'll sample to see what the isotope mixture is. And so if we find it has a bunch of carbon, we'll measure the average weight of carbon, and we'll find if it's a little bit higher, it must have come from this one planet. If it's a little bit lower, it must come from a different one. In fact, there's an entire class of meteorites where they test the carbon because somewhere billions of years ago, a massive collision happened in the solar system, broke off billions and billions of small rocks from the same object, and those keep crashing to Earth to this day. So we can test them all, and we can say, hey, even though these are spread out over millions of years on Earth, they all came from the same object. They've just been falling down on us slowly over time.